Welcome to the next session. Now in this session, we discuss 4 questions from classroom workbook followed by the third module of calculus, that is vector calculus, right? Let us start the session with question number 60. The value of the integral I equal to 1 by square root of 2 pi into integral 0 to infinity e power minus x square by 8 dx is, options are given, 1 pi to 2 pi. Let us see this. Now here we have limits from 0 to infinity. Here this is e power minus x square by 8. Now this is related to gamma function. So to evaluate this integral, take x square by 8 equal to some new variable. So same limits will work. Upper limit of p is infinity square by 8 infinity. Lower limit of p equal to 0 square by 8. This is 0. Now let us simplify this integral. X square by 8 is p. So x square equal to 8p. Differentiate this, 2x dx equal to 8 times dp. Therefore dx equal to 4 dp divided by x. So this is 4 divided by, what is x square root of 8p. So therefore dx equal to 4 divided by square root of 8p dp. That means x is converted to p, so dx must be converted to dp. Now let us evaluate this integral. I equal to 1 by square root of 2 pi into integral 0 to infinity. Same limits are working. E power minus p. Here this dx is this 4 divided by square root of 8p dp. Now square root 2 into root 8, root 16. Root 16 is 4, so it will be cancelled with this. So therefore this is 1 by square root of pi into integral 0 to infinity e power minus p into this 1 by square root of p, we can write it as p power minus 1 by 2 dp. Now this is 1 by square root of pi into integral 0 to infinity e power minus p into this minus 1 by 2, we can write it as 1 by 2 minus 1 dp. So this is 1 by square root of pi into, this is gamma of 1 by 2. But gamma of 1 by 2 is root pi, so cancel out this, the result is 1. See, when we were solving many questions based on gamma functions, every time it involves gamma of 1 by 2, either directly or indirectly. Such an important factor, the value of gamma of 1 by 2 is. Okay, so note down these points. Now next we move to question number 61. The value of integral 0 to infinity, the value of integral 0 to infinity e power minus y cube into y power 1 by 2 dy is blank. E power minus y cube into y power 1 by 2 dy is blank. Now let us handle this. Limits are flexible to apply gamma function. So here minus y cube is there. So take p equal to y cube. So therefore when p equal to y cube, what is dp? 3y square into dy. When p equal to y cube, this y equal to p power 1 by 3. Y equal to p power 1 by 3. So even in place of this y, you can write like this. But here you can see, from this expression we can write dy equal to dp by 3y square. So this expression is dp by 3 into, here y is this, so y square becomes p power 2 by 3. So we got dy in terms of dp. We got p value, y value in terms of p. Therefore this integral will be reduced to integral 0 to infinity e power minus p into, what is this y value? Y value is p power 1 by 3. So therefore this is p power 1 by 3 whole power 1 by 2 into this dy is this dp divided by 3 times p power 2 by 3. Now therefore this is integral 0 to infinity e power minus p into This is p power 1 by 6 into dp divided by 3 times p power 2 by 3. So 3 is constant, we can take before integral 1 by 3 into integral 0 to infinity e power minus p into this is p power 1 by 6 minus 2 by 3 dp. Now what is this 1 by 6 minus 2 by 3? Here LCM is 6. 1 minus, this is 2, 4. So minus 3 by 6, it is minus 1 by 2. So this is 1 by 3 into integral 0 to infinity e power minus p into this expression is minus 1 by 2. Now this is 1 by 3 into integral 0 to infinity e power minus p into this minus 1 by 2, we can write it as 1 by 2 minus 1 dp. Now this is a gamma function where n value is 1 by 2. So therefore this is 1 by 3 into gamma of 1 by 2. So the value is square root of pi divided by 3. Square root of pi divided by 3. Simple application of gamma function. Note down this calculation. Now let us move to question number 62. The integral 1 by square root of 2 pi into integral minus infinity to plus infinity e power minus x square by 2 dx is options are given. Let us handle this. Here limits are ranging from minus infinity to plus infinity. So check whether the given function is even or odd. This is an even function because we have power of x is 2. So this is an even function. So therefore this integral becomes 1 by square root of 2 pi into 2 times integral 0 to infinity e power minus x square by 2 dx. So therefore this is square root of 2 by pi into integral 0 to infinity e power minus x square by 2 dx. Now it will be reduced to gamma function by taking x square by 2 equal to p. So let p equal to x square by 2. So dp equal to 1 by 2 into 2 dx. So 2x dx, 2 and 2 will be cancelled. So dp equal to x dx. But the value of dx is dp by x. So dp divided by what is x value? Actually when p equal to x square by 2, x square equal to 2p. So this implies x equal to square root of 2p. Therefore this x is nothing but square root of 2p. So just assume that this is some new variable p. Same limits will work. So when p equal to x square by 2, infinity square by 2, upper limit is infinity. So upper limit of p is infinity. Lower limit of p is again 0. Therefore when p is x square by 2, dp is this x dx. But dx is dp by x. What is x value? Square root of 2p. Now let us do all these changes. So square root of 2 by pi into integral 0 to infinity. This is e power minus p into this dx is replaced by this dp by square root of 2p. Now square root of 2 will be cancelled. So 1 by square root of pi into integral 0 to infinity e power minus p into p power minus 1 by 2 dp. So this is 1 by square root of pi into integral 0 to infinity. This is e power minus p into this minus 1 by 2 is written as 1 by 2 minus p, 1 p. So many times we have come across with this condition p power minus 1 by 2. Minus 1 by 2 we can write it as 1 by 2 minus 1. Now this is 1 by square root of pi into this is gamma of 1 by 2. But gamma of 1 by 2 is root pi. So the answer is 1. Which of the following integrals is unbounded? Unbounded means an integral which gives infinite value. Bounded means limited area. Unbounded means you cannot measure area value. Let us see options. The first option is integral 0 to pi by 4 tan x dx. Now let us simplify this integral. Integral tan x is log secant x. Limits are from 0 to pi by 4. Secant pi by 4 is root 2. So log root 2 minus secant 0 is 1. So log 1. So this is nothing but log root 2, which is a finite value. So therefore this is a bounded integral. This is a bounded integral. Now look at option B. What it is? Integral 0 to infinity 1 by 1 plus x square dx. When you simplify this, this is tan inverse x. Limits are from 0 to infinity. So this is pi by 2. So this is also a bounded integral because the value is finite value. So this integral is a bounded integral. When you look at option C, this is integral 0 to infinity x into e power minus x dx. This is what integral 0 to infinity e power minus x into this x power 1, I can write it as x power 2 minus 1 into dx. Now this is a gamma function, but gamma value for 2. Gamma of 2 is 1 factorial, so this is 1. So this integral is also finite value, so this is again a bounded integral. Therefore, the first three options are bounded integrals. Therefore, ultimately option D is unbounded. So the required answer is D. This is an unbounded integral. This is an unbounded integral. Option D. Note down this. Now with this, we have finished the chapter 3 module integral calculus. Now let us move to last chapter, that is last module of calculus. We have basically three categories of calculus: differential calculus, integral calculus, and vector calculus. 2 chapters are over. Now the third chapter of calculus part is vector calculus. Now in this we discuss basic concepts, definitions. So the third category of calculus is vector calculus. Now in this session we discuss the basic definitions like definition of vector, scalar, dot product, cross product, etc., followed by some examples. Okay. Particularly this vector calculus concepts are very powerful for electrical people, electronics and instrumentation engineering people because this is a prerequisite for electromagnetic transmission lines or electromagnetic fields. Okay, this is the base for electrical and electronics people, even instrumentation engineering people. Very powerful topic, vector calculus. Let us start with the definition of vector. What is a vector? A quantity which has both magnitude and direction is called a vector. Generally, we have two types of physical quantities, vectors and scalars. Suppose let us consider a body. Suppose one object is moving in different directions, from south to north or northeast, something like that. So whenever a physical quantity has both magnitude and direction, then it is called a vector quantity. That means a quantity which has both magnitude and direction, and such quantities are called physical quantities are called vectors. What is an example? Velocity is a vector. Velocity is a vector because whenever we say the body is moving in this direction with this speed, the body is moving in this direction with a speed of 30 kmph, like that. So we always mention the speed of, we always mention direction when a body is moving in different directions. So directions are very powerful. Therefore, a physical quantity which has both magnitude and direction is called a vector. The best example is velocity. Note this point. Definition: vector. A quantity which has both magnitude and direction. A quantity which has both magnitude and direction is called a vector. A quantity which has both magnitude and direction is called a vector. Example, velocity. A quantity which has both magnitude and direction is called a vector. The example is velocity. Next definition is scalar. Now when you look at scalar, they are basically physical quantities which has only magnitude. Direction is not an important issue, because even if you take any direction, those properties will not change. Suppose if you ask me what is the weight of yours, then I will say that 72 kgs. I can't say that 72 kgs in the x direction or 72 kgs in the y direction or 72 kgs in the z direction. So irrespective of direction, my weight is always fixed. Yes or no? Even you take different directions, my weight is fixed. Therefore, a quantity which has only magnitude but no direction is called a scalar. A quantity which has only a magnitude but no direction is called a scalar. The best example is weight. Write this point. A quantity which has only magnitude but not direction. A quantity which has only magnitude but not direction is called a scalar. Is called a scalar. Example is weight. Example is weight. Next we discuss the definition dot product. Suppose we have two vectors. Generally vectors are represented by the directions like these symbols. A bar is this. A1 I bar plus A2 Z bar plus A3 K bar, comma B bar equal to B1 I bar plus B2 Z plus B3 K. We have two vectors A bar and J bar. Now what are all these I bar, J bar, K bar? Basically, when you consider 3D coordinate system, this is x axis and this refers to y axis, and z axis will be in this direction. So in this direction the unit vector is I bar. In this direction the unit vector is J bar. In this direction the unit vector is K bar. I will discuss what are unit vectors maybe after some time. So assume that these two are vectors. A bar is this, D bar is this. Basically this can be equivalent to a three-dimensional point. This is A1 comma A2 comma A3, and this vector is equivalent to the three-dimensional point B1 comma B2 comma B3. Now we have two vectors A bar and B bar. So the dot product of these two vectors is denoted by this A bar dot B bar. So this is nothing but a dot product. Dot product. So the dot product of these two vectors is given by A1 dot B1 plus A2 dot B2 plus A3 dot B3. Now when you simplify this expression, we don't have any directions. No I bar, no J bar, no K bar on the right hand side of this expression. So purely this is a scalar expression. So therefore the result is the dot product of two vectors is always a scalar. This is my vector. This is my vector. So first vector represents a 3D point A1, A2, A3. Second vector represents a 3D point B1, B2, B3. So the dot product of these two vectors is given by A bar dot B bar, which is defined as A1, B1. This is normal multiplication. This is normal multiplication. Normal multiplication, and it refers to normal multiplication. A1 dot B1 plus A2 dot B2 plus A3 dot B3. And this expression is a scalar quantity. So the conclusion is the dot product of two vectors is always a scalar. Let us take an example. Suppose I have a vector A bar equal to I bar minus 2J bar plus 3K bar. B bar equal to 2I bar plus J bar minus 4K bar. Now the dot product of these two vectors is A bar dot B bar equal to components. Here it is 1, this is 2. 2 minus 2 into 1 minus 2, 3 into minus 4, this is 12. Therefore this quantity is minus 12. So write these points. dot product. Heading is dot product. Let A bar equal to A1I plus A2J plus A3K, A1I plus A2J plus A3K, comma B bar equal to B1I plus B2J plus B3K. B bar equal to B1I plus B2J plus B3K. Be any two vectors. Be any two vectors. The dot product of A bar comma B bar. The dot product of A bar comma B bar is denoted and defined as the dot product of A bar comma B bar is denoted and defined as A bar dot B bar equal to A1 dot B1 plus A2 dot B2 plus A3 dot B3. A bar dot B bar equal to A1 B1 plus A2 B2 plus A3 B3. Work out this example. A bar B bar and the result A bar dot B bar. Note. The dot product of two vectors is a scalar. The dot product of two vectors is a scalar. Now, when you look at this A bar dot B bar, these are normal numbers or they can be functions of x or functions of y or functions of z. Here this A1 dot B1 is also same as B1 dot A1. A2 dot B2 is same as B2 dot A2. This A3 dot B3 is same as B3 dot A3. Because this is normal multiplication. These components A1, A2, A3, B1, B2, B3, they can be a real numbers or functions of x or functions of y or functions of z. But when these are purely scalar quantities. So therefore A1 dot B1 is this, A2 dot B2 is this, A3 dot B3 is this. Now basically this expression is B bar dot A bar. So the result we have is A bar dot B bar equal to B bar dot A bar, and this property is called commutative property. Commutative property. That means vectors satisfy commutative property with respect to dot product. Note. A bar dot B bar equal to B bar dot A bar. A bar dot B bar equal to B bar dot A bar. For any two vectors A bar and B bar. For any two vectors A bar and B bar. That is, vectors satisfy commutative law. Vectors satisfy commutative law with respect to dot product. Vectors satisfy commutative law with respect to dot product. Next we discuss another type of product, that is cross products. Next definition is cross product. Let us see, actually dot product is denoted by dot symbol, cross product is denoted by this. When we were in the normal level, that means school standards, generally we used to have multiplication tables. We used to write like this, 2 cross 3. When you go through multiplication tables at your childhood, you refer 2 cross 3. So it gives 6. But when you grown up frequently, you will go through write like this. So you will be habituated to write the notation like this, 2.3. But both will give same result. 2 cross 3 is 6. 2.3 is 6. But this is a dot product, this is cross product. That means we have some variation in this. So here these two are scalar expressions. 2 and 3 are scalars. 2 and 3 are scalars. So when you apply dot product as well as scalar, when you apply dot product or cross product between two scalars, the result is same. You won't understand what is the difference. But you can understand the difference easily between dot product and cross product if they apply between vectors. Let us see. Here we have two vectors A bar and B bar. The cross product of these two vectors is denoted by this, A bar cross B bar. So here sequence is important. When you write A bar first, B bar second, then this result will be a 3 by 3 determinant. The first row is unit vectors I bar, j bar, k bar. The second row is components of first vector. What are the components of first vector? A1, A2, A3. These are the components of first vector. So we can write A1, A2, A3. So at last we wrote B bar. So in the last row we need to write the components of B bar. So this is B1, B2, B3. And you know how to expand that of this 3 by 3 matrix. Okay. So the cross product of this is this. Suppose when you write B bar cross A bar. So this is again 3 by 3 det value. So first row is unit vectors I bar, j bar, k bar. Second row is components of B bar. So they are B1, B2, B3. Last row is components of A bar. They are A1, A2, A3. Now look at the difference between this and this. Here first row are same. But here second row becomes third row and third row becomes second row. We all know that when two rows are exchanged one time, the det is affected by negative sign. Got it? Therefore, the difference between this and this is so change of second and third rows. Therefore, A bar cross B bar is equal to minus of B bar cross A bar. So this is one useful result. What does it mean is vectors do not satisfy commutative law with respect to cross product. This is one useful result. And another result is when you expand this, this is a vector quantity. That means the cross product of two vectors is always a vector. So one useful point is the cross product of two vectors is a vector, and second one is vectors do not satisfy commutative law with respect to cross product. So this is the basic difference. When you apply dot product between two vectors, the result is a scalar. When the cross product is applied between two vectors, the result is vector. So they are completely different issues. Okay, note this point. The cross product of A bar comma B bar. The cross product of A bar comma B bar. Already we wrote A bar and B bar in the definition of dot product. So I am using same vectors. The cross product of A bar and B bar is denoted and defined as A bar cross B bar equal to det of I bar, J bar, K bar, A1, A2, A3, B1, B2, B3. I repeat once again. The cross product of vectors A bar comma B bar is denoted and defined as A bar cross B bar equal to this. Next you write this followed by this point. Note 1. The cross product of two vectors is a vector. The cross product of two vectors is a vector. Second point, vectors do not satisfy commutative law with respect to cross product. Vectors do not satisfy commutative law with respect to cross product. Next definition, divergence. Suppose we have a vector A bar equal to A1 I bar plus A2 Z bar plus A3 K bar. This is my vector A bar. Now the divergence of this vector is denoted by div A bar. So we can discuss divergence for vectors. This is my vector. The divergence of this vector is denoted by this div A bar, which is given by the dot product of del bar and A bar. This is a del vector, del bar, which is given by dou by dou x I bar plus dou by dou y z bar plus dou by dou z k bar. So this is called del vector. So dot product a1 I bar plus a2 z bar plus a3 k bar. So therefore basically this del vector is obtained by taking partial derivatives as components, dou by dou x, dou by dou y, dou by dou z. So this is called a del vector. This is called as a del vector. Now apply dot product. So therefore this is dou a1 by dou x plus dou a2 by dou y plus dou a3 divided by dou z. So this is dou a3 by dou z. So therefore divergence of the vector a bar is del bar dot a bar. This is a del vector. Let us take an example. Suppose I have an vector r bar equal to xi bar plus yj bar plus zk bar. Now let us find its divergence. Divergence of r bar equal to dou by dou x of I bar component is x plus dou by dou y of j bar component is y plus dou by dou z of k bar component is z. Dou by dou x of x, dou by dou y of y, dou by dou z of 1. So this is 3. Therefore the divergence of r bar is 3. Here r bar is called a standard position vector. R bar is called a standard position vector, which is very useful in the analysis of line integrals, which is very powerful in the analysis of line integrals. So divergence of R bar is 3. This is very important. Okay. First write the definition. Let A bar equal to A1 I bar plus A2 Z bar plus A3 K bar. Let A bar equal to A1 I bar plus A2 Z bar plus A3 K bar be any vector. The divergence of A bar is denoted and defined as div A bar equal to del bar dot A bar. This is read as del bar dot A bar. So work out this followed by this example.